Welcome to BSc Main Physics. Semester 6, Paper 1, Solid State Physics. Today, the class is S55, Problems of Three Magnetic Vectors, Unit Magnetic Properties of Materials, Unit 5, Solid State Physics. Problems of Three Magnetic Vectors. So, in the previous class, we have seen the magnetic vectors B, H, and I, or M. And also we have studied the permeability and susceptibility, and today we see some problems based on them, based on permeability, susceptibility, magnetic flux density, H field, and magnetization. We do some problems, and the first problem is problem number 1. The magnetic field in silicon is 1.2 into 10 raised to 5. You read as 10 raised to 5 ampere per meter. Calculate the magnetization and flux density in silicon if its magnetic susceptibility is minus 4.2 into 10 raised to minus 6. Also compute their relative permeability of the relative permeability of the material. You see, the magnetic field in silicon is 1.2 into 10 raised to 5 ampere per meter. Calculate the magnetization and flux density in silicon if its magnetic susceptibility is minus 4.2 into 10 raised to minus 6. Also compute the relative permeability of the material. ഇവിടെ മാഗ്നറ്റിക് ഫീൽഡൊക്കെ തന്നിരിക്കുകയാണ്. നമുക്ക് പെർമിയാബിലിറ്റി കാരണം ഇപ്പോൾ ഡയറക്റ്റ് ആപ്ലിക്കേഷൻ ഓഫ് ഫോർമുലയാണ്. യു സി ഹിയർ permeability of the material we can find first. Permeability of the material, and for that H field is given as 1.2 into 10 raised to 5 ampere per meter, and psi is minus 4.2 into 10 raised to minus 6, and magnetization, M is magnetization, we have to find, and you know psi is M by H, or M is psi H on cross multiplication. M is minus 4.2 into 10 raised to minus 6 into 1.2 into 10 raised to 5, that is H field. We get minus 0.504 ampere per meter. Negative sign shows the magnetization is opposite to the field. That is the meaning of negative sign. Now we can see flux density. Flux density B is equal to mu 0 H plus I, or H plus M. Magnetization we also write using symbol M. Therefore B is mu 0 into H plus M, that is 4 pi into 10 raised to minus 7 into 1.2 into 10 raised to 5 minus M that we have calculated, minus 0.504. The answer is 0.151 Tesla. That is flux density of the material. Then we can see what is relative permeability. Relative permeability we see, which is mu r 1 plus I 1 plus minus 4.2 into 10 raised to minus 6, which is equal to 1 minus 0.0005042. We get 0.9999 etc., which is nearly equal to 1. Now we see another problem. A rod of magnetic material 0.5 meter length has a coil of 200 turns wound over it uniformly if a current of 2 ampere. You see it again. A rod of magnetic material 0.5 meter length has a coil of 200 turns wound over it uniformly if a current of 2 ampere is sent through it. Calculate the magnetic field H, A part, B part, intensity of magnetization, M vector, and C, magnetic induction, B, D, relative permeability, mu r of the material. Direct question. psi is equal to 6 into 10 raised to minus 3 is also given. Answer A part B is equal to B0 Ni. നമ്മൾ സോളിനോയിഡ് ഈ ഇലക്ട്രോഡൈനാമിക്സിൽ പഠിക്കുന്നതാണ് സോളിനോയിഡ് ഫീൽഡ് വെൽ ഇൻസൈഡ് ദ ഫീൽഡ് വെൽ ദ ഫ്ലക്സ് ഡെൻസിറ്റി വെൽ ഇൻസൈഡ് എ സോളിനോയിഡ് ഈസ് mu0 Ni. So we write that relation here, but B is mu0 H. That is definition of B in vacuum. So we equate these two. Equate these two, we get mu0 H is equal to mu0 Ni or H is Ni. That is a solenoid field. When a current I passes through a solenoid, the H field is given by Ni, and it can be also written as H is equal to N by Li. Small n is number of turns per meter of the solenoid, and if there are capital N turns on a length L, H is N by L. So we write H is N by L into I. Small n is capital N by L. Therefore, H is N by L into I. And here, N is 200, L is 0.5, I is 2 ampere. Put the values. H is equal to 200 into 2 current by 0.5, which is equal to 800 ampere per meter. B part, magnetization M, that is psi H. Psi is M by H, M by H you know. So M is equal to 6 into 10 raised to minus 3, that is given into 800, which is 4.8 ampere per meter. Then we can find the mild flux density using relation B is mu0 into H plus M. That is equal to 4 pi into 10 raised to minus 7 into 800 plus 4.8. That is 4 pi into 10 raised to minus 7 into 8 not 4.8. That is 1.08 into 10 raised to minus 3 Tesla or Weber meter raised to minus 2. Weber per meter square. And mu r is relative permeability. Mu r is 1 plus psi. 1 plus 6 into 10 raised to minus 3. 1 plus 0.006 equal to 1.006. Next problem. A magnetic field of 4000 ampere per meter produces a flux density of 16 pi Weber meter raised to minus 2 in a bar of iron. Calculate the relative permeability and susceptibility of the material. You look here again. A magnetic field of 4000 ampere per meter produces a flux density of 16 pi Weber meter raised to minus 2 in a bar of iron. Calculate the relative permeability and susceptibility of the material. Here H is 4000 ampere per meter, B is 16 pi Weber meter raised to minus 2. That we give here, that is B is equal to mu is B by H. That is 16 pi by 4000 equal to 0.004 pi equal to 0.01254 ampere per meter. Then comes relative permeability mu r, that is B by mu0, 0.01254 by 4 pi into 10 raised to minus 7 equal to 10 raised to 4. Susceptibility psi is equal to question mark, mu r is 1 plus psi is mu r minus 1, that is 10 raised to 4 minus 1. That is 10,000 minus 1, which is 9999. That is psi. Now comes electron theory of magnetism. Electron theory of magnetism, and here we see two magnetic moments. Electron theory of magnetism, a short answer question, important. Two magnetic moments of atom. ആറ്റത്തിൻ്റെ രണ്ട് മാഗ്നറ്റിക് മൊമെൻറ്റ് ഏതൊക്കെയാണ്? എല്ലാ ആറ്റത്തിനും രണ്ട് മാഗ്നറ്റിക് മൊമെൻ്റ് ഉണ്ട്. രണ്ട് തരം മാഗ്നറ്റിക് മൊമെൻ്റ് ഉണ്ട്. ഏതൊക്കെയാണ്? വാട്ട് ആർ ദി ടു മാഗ്നറ്റിക് മൊമെൻറ്റ്സ് ഓഫ് ആറ്റം? Electrons in an atom have two kinds of motion, namely the orbital motion and the spin motion. Spin motion. Due to the electron motion, atom has two magnetic moments. Electron motion മൂലം ആറ്റത്തിലെ രണ്ട് magnetic moment ഉണ്ട്. They are one orbital magnetic moment mu L and two spin magnetic moment mu S. രണ്ട് തരം മാഗ്നറ്റിക് മൊമെന്റ് ആണ് ഉള്ളത്. Number one, orbital magnetic moment. Orbital magnetic moment mu L. It is given by the expression mu L is E by 2 into L vector, capital L vector, where capital L is the orbital angular momentum. ഇപ്പം mu L orbital magnetic moment കാണുന്ന ഇക്വേഷൻ ആണ് mu L is E by 2 into L vector, capital L vector. L vector is the orbital angular momentum of the electron. But L vector is L into h by 2 pi, where L is the orbital quantum number. So we put here mu L is E by m into L into h by 2 pi. Mu L is L into E h by 4 pi m. If you take the lowest value for L, lowest value is 0, but when we take 0, mu L vanishes, so L will take 1. L value varies from 0 to higher values, 0, 1, 2, 3, etc. That is L value. So when we take L value 1, we get mu L is 1 into EH by 4 pi m. EH by 4 pi m is a very important term that we see. Now comes spin magnetic moment. Spin magnetic moment mu S. Mu S, it is given by the relation mu S is E by m into S vector, capital S vector, where capital S vector is a spin angular momentum. Spin angular momentum is smallest in h by 2 pi. Capital S is smallest in h by 2 pi, where smallest is spin quantum number, which is half. So capital S vector is equal to half into h by 2 pi, h by 4 pi. That we put here, we get mu S is E by m into h by 4 pi. That is also here mu S is equal to EH by 4 pi m. EH by 4 pi m is a very important term. It is called the Bohr magnetone that we see in the next class. With this class number 55 is over. We continue our class. Thank you very much.